Hello everyone, welcome to lesson 4 Logarithms and Exponential Functions of Risk Hub Quant Primer. Today we'll be learning about what are logarithms, what are exponential functions, and not just what they are, why they're used, what's the intuition behind them, not the mathematical formulas, not the mathematical jargons, but the actual things, why these things exist, and how are they used in the world of finance, let's say, and what's the intuition behind them, what do we actually use them with, because in finance, whenever you'll be calculating continuously compounding returns, whenever you will be calculating your future value of the money you have right now. I have these $100,000 right now. What will be the value in, like, let's say 10 years if they're continuously compounding? What's the number that you use? What's the function that you use? What are the things that are used to understand how this growth is happening? Those things are taken with logarithms and exponential functions. That's it. Let's go with it. Let's start. What's the easiest analogy that we can find here? And let's understand what these functions actually stand for. Give me a second. So let's continue with what we were saying here. Oh, okay. Yeah. This. So let's understand what exponents and logarithms actually are for their basic sense, not the mathematical intuition. So, let's say there's a plant that grows. Okay. Let's not take a plant right now. Let's take a number that grows. Let's say 2. Now, 2 doesn't grow by plus 2 every time. It doesn't go plus 2. It grows into 2. 2 into 2 into 2 into 2 into 2 every time. It doesn't go plus. It doesn't go like this. It's 2, then it's 4, then it's 6, then it's 8, then it's 10. It doesn't go like this. It goes 2, and then it goes 4, and then it goes 16, and then it goes 32, and then it goes 64. This growth is exponential. When we talk about, no, what is exponential growth? This is exponential growth. This is linear growth. And this is what we are talking about. This is exponents. Now, I talked about, okay, this is exponential growth. But how many jumps did it take for me to get to this growth? That is told by log. That's the logarithm function. That tells me how many jumps are taken to get to this number that we are here, that we are up here right now. Okay. Now, let's see about the exponential functions. So what are exponential functions? When, let's say, there is a variable in the power of the function, like y is equal to a raised to power x. So this is some constant number. Let's say it's 3. But when it's x, like the variable increases, the function increases. It's not y is equal to x raised to power 3. It's y is equal to 3 raised to power x. So every time this variable increases 1, 2, 3, 4, the number multiplies by 3. This goes like this number. Okay. It became a straight line, but it's meant to be a very steep curve because it's just going up like this now. That's an exponential function. The most commonly used exponential function in the world of finance is EX. Why? Well, okay, first of all, let's talk about this E. It's a Euler's number, and this Euler's number is 2.71828. That's it value. That's its value. You will not have to calculate it like this, like punch 2.71828, then raise it to the power. You have the function very much alive in your BA2 plus calculator. Even the log x function. log x function is given as lnx in your calculator. So that's how you will be using it in calculators. What's the benefit of using them? How are they used and what do you get? Okay. So first of all, let's say about EX. It helps in your continuously compounding growth. It's a number that helps you with continuous compounding growth, continuous growth, and in stochastic processes. This number helps you with those. What are the financial examples about this? So when you calculate your future values, we'll do this in next chapter. When you calculate future value of the money you have right now, let's say you have $100,000 right now. Right now, let's build this a timeline and it's T0 and it's T10, basically after 10 years. If your money grows at a constant rate, it grows every single second. It's not just day or night, it's every single second. Whenever you blink, your money is growing. Then what's the at a 5% per annum continuously compounding rate? Then what is the money that you will have in 10 years? How do you calculate this? Future value is equal to present value, which is $100,000, into e raised to power rate into time. And this is how you get your future value for this $100,000 continuously compounding at the rate of 5% per annum for 10 years straight. And it's going to be an exorbitant number that cannot be fathomable. That's not a fathomable number, but it will be there. And that's the reason these exponents x are used to get the continuous compounding returns. Now, what is a logarithm? A logarithm, okay, we talked about base C in finance. It's a number that helps in continuous growth. Delving deeper into the mathematical sense of this number will mean that, okay, so there's this derivative thing. What does derivative differentiation thing? It tells you about what's going to be change in the number with the change in x. Let's say uh, how much the price of the bond changes when the yields change by a little, how much the speed or time of the travel changes when the speed changes. So these functions, there is a derivative concept. Okay, so let's say dEx by dx. The answer is Ex only. It doesn't change. In respect of x, this doesn't change a lot. And so the answer remains the same. And the mathematical sense of this derivative is, uh, okay, that you will learn a few things. It's x d by dx and it becomes x only. So yeah. Now let's go with the logarithm function. What is a logarithm function? A logarithm function is inverse of the exponential function, inverse of ex. You wanna see how? Okay. Put log ex and the answer will be x. Put e raised to power log x, answer will be x. If you plot a graph for ex and log x, I'm so sorry. I just have this cold right now. Okay. So this doesn't touch. This is a ex number. It doesn't touch this line minus x-axis. It goes closer to 0 but doesn't touch it. And at x is equal to 0, the value of y is 1. How now you'll see y. So e raised to power 0 is equal to 1. Any number raised to power 0 is equal to 1. So e reaches 1 when it's 0, the y value. And the log value is like this. It doesn't touch the y-axis, negative y-axis, but it goes like this. And if you see, this is an inverse. This is this symmetry there. This is the ex function and this is the log x function. And they are inverse of each other. That's the logarithmic function. When calculating continuous returns, you will be using log returns. So let's say it's R. You want to calculate there is change in 55 over 50. Okay, the starting rate was 50. The starting rate was 50, and then it raised to 55. What's the return over here? Normally, the discrete will be 55 minus 50 divided by 50. Uh, it gives you 10% return. What will be the log return? Log return will be R2 minus divided by R1 is equal to okay, what will it come like? 55 divided by 50 log. It will be 0.0953%. So when this number compounds continuously at this rate, then you will get this 55 number. When it compounds discretely, then the number is 10%. This is how logs are used. Now let's learn about some key logarithm rules that we have here. We have product rule. First rule is product rule. So log AB is equal to log A plus log B. Okay. Ln and log are the same thing here. Log. The other is quotient rule, where log A divided by B is equal to log A minus log B. The power rule, log A raised to power B will be B into log A. So these are the three rules that we have in calculating of logs. This is the power rule. So when log has something in multiplication, you can add them distinctly. When it's a quotient, then you have log A minus log B. And when it's a power mode, then it's the power goes in front of log and it becomes B into log A. That's it. That's how easy it is. And this will be helping you in solving a lot of questions. Now let's calculate some returns right now. I made this example. So put in it log returns versus simple returns. We take two things, okay? So this and this, you'll see something. T is equal to 0, T is equal to 1, T is equal to 2. The price at T0 was 50, the price at T1 is 55, and the price at T2 is 62. All right, works. Easy as it is. Okay. Now let's calculate returns. What will be the simple return for the first time period? Okay, simple log. For the first time period, the simple return will be 10%. For the second time period, the return will be somewhere 7 divided by 55. It will be 12.72%. And the like return for both of the 2 years will be 62 divided by 50 gives out to be 24% return. Now with log return, 55 divided by 50 log, it gives us 9.53%. 9.53%. And for second part, it gives out to be 62 divided by 55 log, 11.98%. And when we calculate this totality mean log 21.51%. Yeah. If this return These returns are very close, 9.53%, 10%, 12.72%, 11.98% are very close right now because this is a very small number we are talking about. The changes are not that big. So that's why the numbers are not even that different. Yes, there is a point one per there's a 1% difference, but that makes sense right now. It's not too much of a difference. But now look at the aggregation. The aggregation of these numbers will give you perfectly 21.51%. The log returns are additive. They're continuous, they're additive, and that's why modeling them statistically is so easy and useful. Whereas simple returns, okay, it's easy to calculate them more easy to understand. That there's 10% growth in the first year, then there's 12.72% growth in the second time period. But the ideal growth, the ideal, it's not additive. You cannot add it and you cannot get 24%. That's just not possible. You cannot even easily find out the average of these returns for the two periods. That's what you can do with your log returns. So log versus simple, always choose the log returns because for continuous growth. To model the analysis, log returns are preferable. To model your returns, logs are preferable. If you want to show it in a like presentation or something, then simple returns are more intuitive and helpful to the people. Exponents and logarithm functions. So let's solve a logarithm question. Let's solve something. So okay, let's take an example. I have some amount, let's say 500 right now, $500. In 2 years, in 2 years, this amount becomes $800. I want to know this continuously compounding rate. So let's put in the formula. What's the formula? FV is equal to PV into E raised to power RT. That's the formula. That's the continuously compounding. 800 is equal to 500 into e raised to power rt. T is our 2. So 800 is equal to 500 dot e2r. Now what do? We calculate 800 divided by 500 e2r. 800 upon 500. 800 divided by 500. 1.6. Now what do I do? I know log cancel. I have to like take off the e number. I have to do that. So what I'll do is I'll take log of 800 divided by 500 is equal to log of e to r. What will I be left with? Here I'll be left with 40.47, and here log and e cuts each other. What do I get? 2r, and then for r I get 0.47 divided by 2, which is 23.5%. So for 1 year return, I'm getting 1 year continuously compounding rate return of 23.5% per year, per time period. And this is how my $500 becomes $800 in 2 years with this rate. This is how you calculate the numbers. This is how easy it becomes when you're working with these numbers. And that's where exponential and logarithm functions are used. Thank you so much. Let's meet in the next lesson.